All right, there we go. I'm Joshua. I'm giving a talk about reverse engineering. And reverse engineering is how to read programs without the source code. So this talk is online. I'll post the link in chat so everyone can see it. And you guys know where the GroupMe is, or you wouldn't be watching the talk. The Discord is. Okay. So what is reverse engineering? Reverse engineering is you take some program that's running on your machine that you haven't seen the source code for, right? You just want to know what it does. And you figure out how it works. And you're like, why would you do this, right? So there's a few different things you can do with this. The most benign thing is you're writing a compiler and you want to know what the binary you've made is actually doing. And to do that, you have to look at the assembly, because that's what a compiler generates. The security focus aspect is you have some virus that's on your machine and you want to figure out what it's going to do when it runs without actually running it, because that's how you get infected computers. So to do that, you take apart the assembly and see what it would do if you ran it. And you can also run it in a virtual machine and such, but this is if you need to know exactly what it does. The third one is really interesting. So Minecraft originally did not have any mod tools or anything. The way you modded Minecraft is you took the .class files that the Java compiler generated, and you modified those class files in place to do something else. And that's how you wrote mods, is you modified the generated code for Minecraft. There's a whole Wikipedia article about it. You guys can read if you're interested. The next thing is, say you have a benign program and you're trying to bypass a security gate, right? And you can see what the program does and try and work around it. This works best if you have the program in a self-contained environment. Because if you're trying to reverse engineer something with a time limit, it doesn't go super well. It's kind of time consuming. And then the fifth one is, say you're running Microsoft Word or something. Microsoft is never going to give out the source code for Microsoft Word. If you were a malicious company, you could take that binary and see what it was doing painstakingly, one bit of code at a time. Now in practice, nobody does this because it's easier to just write it from scratch than to read the assembly, but in theory you could. All right, so let's take an example of, say you want to know the password for a program, and you try and type in the password and it says no, you're wrong. And what can you do, right? Well, if you have source code, you just look at what the source code says, and we say, all right, there's the password. It's magic super secret constant, and you type it in. But what happens if you don't have that source code? What can you do? Well, the string it's comparing it to, if it's hard-coded in the binary, that means it's in the binary. So it's sitting on your disk right there. So let's go to, I think it's this one here. Printf debug, yeah. So everybody's favorite command is strings, and you just run strings on the binary. Oh, if I could type. And you see all this junk here, and you scroll through it, and let's just filter out the things that start with underscore. Grep. Right. And one of the things you see is magic's different secret string. And you're like, oh, well, that's probably it. And you can type it in, and any string constant that's in a binary you can find with strings. But if you have something that's not a string, it's a little more tricky. If it's a number, what do you do? Binaries are made of numbers. You can't pick out the specific number you're looking for, because it's all numbers. So what you have to do is take apart the assembly. So here's the program that's running in that screencast, a.out, and you type in something and it says it's wrong. What you have to do is you have to see what it's actually doing. So I'm going to take a brief digression here. I've tricked you all. This is not a talk about reverse engineering. It is a talk about x86 assembly, because that's what you have to know to do reverse engineering. So what is going on in your program that you've compiled? There's four main parts. There's the stack, which is local variables, int I or x or whatever. There's heap, which is things that live longer than the current function. So say you have, I don't know, like you return a string from a function. That string has to be somewhere in memory, right? If you return a value, then it has to be somewhere so that the other function can look at it. And that somewhere is the heap. And the heap is just like a region of memory that holds all these long-lived values that live longer than a single function. There's static data. Static data is like data that lives for the entire lifetime of the program. So like string constants and that sort of thing. And literals are basically the same as static data, but read-only. And then there's instructions. And instructions are what are actually running on the CPU. So let's take a look at this program again. And if we say disassemble main is like the main function, the entry point, right? And these numbers here are what the CPU actually sees when it runs your code. And you can think of the CPU as like an interpreter in hardware, and it's interpreting, this binary zeros and ones. All right, and then this is some more information about stack and heap. So there's the stack pointer is like where the current function starts. Yeah, here's your arguments. So say you have like int f or whatever, right? Let me bring up some source code. Right, so this main function is a bad example. All right. Say this was int main and it took arguments, right? In argc. Has everyone taken 240? Do people know like what C looks like, C++?
Currently taking it? Makes sense.
Okay. It's the syntax is mostly the same as Java, even though some of the ideas are a little different. So if you have, argc and argv, these variables have to be somewhere, right? They don't just appear out of nowhere. And the somewhere is this little region of memory here. This is like the previous function's memory here, they used. This arguments is like the region of memory where these arguments live. And then all this stuff about the stack pointer is your local variables. So like these have a specific address on the stack where it stores the value of these variables. Cool. All right, and then some more stuff. So C has an interesting model. So what it does is if you have multiple C programs, this is a bad example because it only has one. Okay, if you see here, there's like a bunch of different C files in this directory, and you can actually compile them one at a time. If you run gcc on response.c, right? What it's doing is it's only compiling this one file. And you can see it made here response.o, but not any other files. And these are called object files. And object files are like a sort of high-level assembly. You can think of it almost. They have. Well, let me run a few more GDB programs, and maybe it'll be more clear. So a.out was our original program here, right? Disassemble main. Okay. And so there's some stuff here about the stack and heap. This is saying save where I was and give me some space for local variables and that sort of thing. So you see here this call q f right. That call q is coming from f put s, right? We're calling a function. But the interesting thing here is if you did the gcc-c thing, right, where does it get printf from? Where does it get f right? Like, that's not in your program. It's part of the standard library, right? But it's not, like, the implementation isn't in these includes. What these includes just have is, like, what the function looks like what arguments you need to call it with, but it doesn't have the implementation. And so, like, where does that come from? So what happens is there's a program called a linker. On Linux, it's called LD. And it takes that .o file that we made. It's like one specific source code file. And it links it to the standard library. And the standard library is usually things. Actually, I can show you. So here is response.o. Oh well, that was a bad example. Okay, here we go. So this is showing you the dynamic dependencies this program has. Now, it might not seem like it's dynamic because you run it and it runs, right? But this LD Linux SO is actually, when you run a.out, it's not run directly by the CPU. LD Linux runs this program. This is an executable. And it's taking your executable and it's running it and it's linking it to the standard library. And that's where it gets that printf from, is from this libc.so. Okay. Right, so you might say, like, what's all this stuff about LD Linux? Can't you just take this SO file and put it in the same file as the one I did, and then they just be together, right? And that works. But if you have, 1,000 programs on your computer, and they all use libc, then you don't want to compile in libc 1,000 times, because that takes up a lot of disk space. So what you can do instead is what's called dynamic linking. And dynamic linking takes a program, it's called a shared object file, but it's basically this .o we saw before, compiled in a special way. And it tells, so your program says, I want libc from somewhere on disk. It doesn't know where that somewhere is. It just says, I want libc.so from somewhere. This is the from somewhere. And then this interpreter here, this LD, is in charge of finding where that somewhere is, which in this case is /lib/something. Okay. Then the other thing, so when you write a C program, you don't really care about all this stuff, right? Like you don't care where the variables live in memory. You don't care like whether the arguments come before the local variables or not. Like it doesn't matter to you. But it matters a lot to the compiler, because if that order were different, if you like put the variables before the function arguments, then suddenly you can't call any of the standard library functions, because the standard library functions expect them to be in that specific order. And if you change that order, then now they're looking at the wrong values, and your program can do anything, and it's not something you want happening. It's called undefined behavior. So this is called the application binary interface, is the order and the specific way that arguments are passed to functions like at the assembly level. This is such a great link, highly recommend. I'm going to put this in chat. Okay. And then, so this isn't like specific to binary programs. Like say you have a TCP packet, that's also an ABI, because it has a very specific format, and you can say I want byte 6, and byte 6 is exactly one thing. But it's you see it come up the most for programs, because there's so many different, because at the library level, it's the ABI matters. And then the Linux kernel has to have a stable ABI, because everything expects, when I call write, I expect it to write to something. So if you change the ABI, suddenly they're doing something else. All right, so now we're going to start with assembly. If you haven't taken 212, that's okay. This is like a 212 crash course. So we have two functions here, and then we have like the int main, and then we call some standard library functions, and then we have a function sub that just does some basic math. And there's all this like stuff going on over here. When the compiler sees this text, it can't run text, right? The CPU understands binary, so it's turning all this text into assembly. This is x86 assembly, which is the one almost everything uses now. Like AMD and Intel and all of them use x86. I think Mac might be switching to a different architecture soon. And anyway, not super relevant to the talk. So there's a few different things you can do in assembly. First off, to do operations on data, you have to have somewhere to store it, right? And the fastest and the simplest storage is registers. So you have like a place on the CPU die that stores some data, and these are some of the places. If you look at this program we had, it's using a lot of these variables, right? It's using RAX and RDI. Sorry, it doesn't say it here, but if you replace all these E's with an R, it's the same register, because x86 is interesting. So it's using all these registers that are listed here to do things. And some registers are more specific than others, but in general, you don't have to worry too much about it.
I have a question, if you don't mind.
Yeah, go ahead.
What's the difference between like a cache and registers?
Okay, so there's a few different places you can store things. You can store them in registers, which is like on the CPU die. It's the fastest way you can access data. You can store them in memory, which is like your RAM, right? It's like it's for the lifetime of the program, but you're not using it right now, so it doesn't need to be as fast. And then there's disk, which is the slowest storage. And then you can get into network and blah, blah, blah. And so what the cache is taking data from memory and bringing it onto your disk is kind of slow. The fastest it can go is light speed. And your CPU operates a lot faster than that. Your CPU counts in nanoseconds. So the time it waits, it spends waiting for the data to come from memory to the CPU is like kind of wasted, right? So what it does instead is it tries to minimize that time by caching the data. It says you looked at this address in memory, 20 milliseconds ago. The data probably hasn't changed since. And that way it doesn't have to look into memory every time. And it speeds up execution. Does that answer your question?
Thanks.
One sec. Okay, so there's different dialects of assembly. x86 is the most common one for consumer machines, but it's certainly not the most common one on, say, a phone. Phones normally run what's called a reduced instruction set computer. And the difference is that CISC is meant like for humans to write, like back in the 80s. And so you can do like 3 different things at once with a single assembly instruction. My favorite is reps move, which is Sterling in one assembly instruction. It's stir copy, sorry. Which is kind of crazy. It's also horrifically slow. Don't use it. But it's a very high level instruction. This is basically a while loop in one assembly instruction. There's no such thing as reps move in a reduced instruction set, because interpreting those complicated instructions takes more time. It takes more energy. If you're on a phone, energy matters a lot. And so they're very simple instructions, and it puts some more burden onto the compiler, but at the benefit of making the CPU simpler and smaller and faster. And these are all the different ways that x86 is complicated. x86 has a lot of backwards compatibility.
I have a question, if that's okay.
Yeah, go ahead.
So, like, as this pertains to reverse engineering, like, are we kind of getting to the point of like, basically, if you do understand assembly, like, that basically opens up like endless doors for reverse engineering?
Correct. Yeah. If
Okay.
the program you have has a one-to-one correspondence with assembly, so if you can read assembly, you can read any binary program. So there's a whole bunch of x86 instructions. We're just going to do the more common ones. Move is move data from somewhere to somewhere, and the somewhere can be either a register or memory or like a constant value. So this says move the constant 0 into the register EDI. You can add things, and then compare is 10 less than EAX. And if so, jump to exit. This is a label, just like in C. And if not, continue. So you fall through. And so this is like a little while loop, right? It's saying while EAX is not equal to 10, keep going in the loop. Otherwise, exit the loop. And this adds 1 to the counter every time. So you can imagine it being the same as this sort of C code, right? While you have your variable edx, and you're saying while edx is it's not equal to 10, add 1 to edx, or like that, right? And then this says move 1 to EAX. With an A, not a D. Right, so this is the C equivalent of this little assembly code over here. There's some other instructions. You can XOR, you can push and pop. So the stack is one, the place in memory where you store local variables, but two, it's also like a regular stack, like a data structure. So you can add things onto the end, and you can take them off very cheaply, because the adding thing onto the end is just incrementing the stack pointer. Let me go back. So the stack pointer is ESP. It's just another register. And what it's storing is where in memory the stack starts. So saying I want more memory on the stack is just adding 8 to the stack register. Let's see an example of that real quick. So if you see here, this sub RSP, that's saying I want 20 more bytes on the stack for my local variables. And then this push and pop is saying store something to this address, like, and the address it means is like implicitly the stack pointer. It says write whatever is at EAX to the address at the stack pointer, and then increment it by 4. 4 is the size of the register. And then you do, and so what this lets you do is you can like say, okay, I want this for later, and then change it and do whatever, and then get it back. And this is really important for calling functions, because otherwise, like, your variables disappear every time you call a new function, which is bad. So you need to save them somehow so the other functions variables don't get clobbered. And then call and return. So you say, all right, call this function, and then EAX is where the return value of the function is stored. So if you have the return 1 in C, right, that's stored in the register EAX. And this is just doing something. So it's moving variables in memory to registers, and then it's returning 1. And then NOP is no operation, and this is a fast way to do math because x86 is strange. I'll come back to these because I want to do some hands-on examples. All right, so here's our printf program. If I could type. Right, and this one has debug symbols, so it's like annotated, right? Let me put the numbers on this side too. Well, they're off by 1. I keep forgetting how to use that now. Anyway, the idea is you can add what's called debug symbols to your assembly, and it'll say which line the assembly came from and that sort of thing. Maybe it's P. Anyway, if I can't figure it out, I can't figure it out. But there we go. Okay, so this, when you declare a variable, that's not just like a thing to the compiler that says this variable exists. It has to actually store that variable somewhere. And that somewhere is 16 minus RBP. So you're saying move 0 into this specific address. And this address is your variable. Like, the spot where it's stored is length right there. And then to call a function is super verbose. You have to move every one of the arguments into place, and then you have to say, okay, this is the function I want to call, and then you have to actually call it. It's not simple like in C. There's like all this setup, right? And actually one of the optimizations a compiler will do is it'll say, well, this function is really small, and the setup takes a lot of like instruction space. What if we just move the body of that function into this function? And that's called inlining, is taking the body of a function and moving it into the function that calls it. And then, so this is like a simple example, right? You say, oh, enter the password, get line, compare it to a constant. And there's all this stuff going on here. So standard in is a global variable in C, because C. And notice how it says the word standard in, right? It's not a number anymore, it's a symbol. And this is going back to our bit about linkers before. Because the standard library is somewhere else that's not your program, the compiler doesn't know the address it's at until you run the program. So what it does instead is it says, okay, I have this symbol that's standard in. And the linker will, at runtime, replace that symbol with the actual address in memory. So it's like there's a lot of pieces working together to make a binary run. And then these are like some other temporaries on the stack. So this is probably line and length right here. And then this is the compiler not being very smart. So it put them in RCX and then immediately moves it to another register to match the calling convention. So what I said about ABI before, that's a type of calling convention. Getline expects its first two arguments to be an RSI and RDI. And if you put them anywhere else, it won't work. And then we've got a little if statement here. Move a value to the register. This is probably line here. And then compare some symbol to it. So LC2 is this string constant here. And if we look down here, oh, well, it's not in the slow snippet here. But I think it's object dump. Yeah, there we go. One of these symbols will be LC2. Stop. And anyway, it's saying I want whatever's at this address to be in RSI. So it's saying take the address of RIP plus LC2 and put it into this register RSI. And the reason it says the address instead of loading the value itself is because a pointer in C is not like a pointer in C tells you where to find a string, right? So stir compare in C says take these two addresses in memory and compare them to one another. So the reason it uses the LEA is it's saying give me the address of the string constant, and then I can compare it to RIX, which is line. We saw it before here. And then it calls error. Error doesn't take any arguments, so notice this is really cheap to do. There's no setup. And then notice how there's a jump here, right? It's comparing EAX to EAX. And what that does is if they're equal, it will go here, and otherwise it will fall through and call error. And then it's doing the same thing similar as before. It says take this string constant, put it here, and then call puts on that string constant. So let's see it in action. This is the same program here, by the way. We've been looking at it. Right, and so it jumps through, and if you got it wrong, then it jumps to error, and error says you lose. All right, so does anyone want to try and figure out what this guy does? I know it's a little long. I don't know if I can get it on one screen. Well, clearly I didn't think this through. One sec. So the tool I'm using is called GDB, which stands for GNU Debugger, I think. And it can do all sorts of cool things with binary programs. I think this is it. Yeah, this looks right. Okay, so who wants to take a guess at what this guy is doing? So we've got the setup from before here, right? This is a new function. This is some stack space this is some space in the stack for the local variables. And then there's like all this stuff here going on. Now, does anyone have an idea like where you'd start or what it's doing? Here's the program itself, by the way. And you type in an integer, and like how would you figure out what this does? Well, you see an F right here, so this is probably where it's printing something, right? So let's you say, so this is saying I want to stop when we get to the main function. And so you run the program, and it stops when you get to the main function. And then layout, we want layout register, right? And this is, GDB is showing us everything that's going on in the registers of this program right now. So you see you've got RAX, you've got all these registers I was talking about before, and it tells you where in the program you are. So currently we're at the very first step, which is give me some space for the local variables. And this says go to the next instruction, and it'll walk through these one at a time. And these are all the registers that changed in the last instruction. So the stack pointer changed. It subtracted 0x20 from it, and the instruction pointer changed. The instruction pointer is this little guy on the side here. It's where you are in the program. This is doing interesting things. All right, and this EAX here, if you XOR anything with itself, you get 0. So RAX gets set to 0, and then it's doing some things with local variables. It looks out like, and this standard out here is the same standard out from before. So it's getting ready to print something to the console. There's like all this setup here again. I forget how to undo layout. Well, maybe there's not a way. Well, we'll come back to it. Anyway, the reason I want to change it is because GDB swallows output in this mode, but if it hadn't swallowed output, you would have seen the thing from before, which is enter an integer. And we can actually find where in the program that is. It's a constant, right? So you can say print that constant. I forget how GDB works, sorry.
Can I raise my hand?
Yeah, go for it.
All right. Do you ever use the X over S?
X over S?
Yeah, type X over S and then the register. Or not the register, but the memory location, sorry.
Like that?
Yeah.
That was the command I was looking for, thank you. And that shows what's at that address in memory. So what's at that address in memory is a string constant, and this X over S is telling GDB to interpret it as a string. All right, and then it's got like some more setup here, which is like local variables, right? It's passing these as arguments to fscanf, and fscanf in C is like how you do input. All right, so it says here enter an integer, right? And so I put in 41, and GDB did not like that. And notice like how all these registers change, right? Like fscanf is doing a lot of things under the hood that we just didn't notice. We skipped right over it. If you wanted to do, this is not a reverse debugger, but if you wanted to step into the function, you could do step I, and that says, okay, I don't want to skip over it. I want to see everything the function does. I'm not doing that here because fscanf is complicated and not particularly interesting. All right, so what's this compare here? EAX is the return value, remember. So this is like the number that we typed in. And notice how it's 41, like I typed in. Oh, well, it's not showing yet. But I typed in 41, and 41 is what's in RAX. And it's comparing it to this string constant here, well, numeric constant. Well, what's this numeric constant? It's 43151. Well, okay, maybe that's the number it's looking for. I think it was 43151. And that's it. And so you can see, like, if you were just looking for a random number in the binary, you'd never find it. But if you step through the instructions one at a time, you kind of get an idea of what's going on. Questions before I go on? Okay. Well, let's do something a little more complicated. This is like a little while loop here. Okay. And we'll do the same thing, you know, break main, stop when the program starts. And this is showing the same thing as before with the registers and the assembly. We walk through it one at a time, it prints something to standard out, This was all set up. It calls fwrite with standard out, and it calls scanf. All right, and so it wants another password here. So let's just put in, I don't know, 51. And it gets here, and it says jump. Well, why is it jumping? We just got here. Let's see. GDB is so odd sometimes. Okay. And it's, so these are like more local variables, right? And it says compare OX31 to EAX. Well, we typed in 51, which is not the same as 49. And it says if what we typed in is less than 49, then go back to where we just were. Or sorry, greater than 49. Right. And then these are like some more local variables, and it does some more compares. These are all in hex because I don't know how to make GDB show them as decimals. And it's doing some things. It says jump if those two were not equal. Right? And then so we got an error here. Call queue error is going to say, oh, you lose. Oh no. So clearly if we type in 52, or type in 41, typed in 51 before, clearly that's not going to work, right? It goes straight through and it says you lose. All right, well, we saw a couple constants before. Let's try one of those. And so run just starts it over from the beginning. And we'll step through again. Whoop. And put in a different number and see what works. And so we saw the magic constant 51 before, so or 52 before, so let's try that. Or GDP is so bad at this job. Okay. Right, so we get here, and remember OX34 is 52, which is the number we typed in. So let's see what happens here. And it's comparing 0 to OX negative C, which is like some variable on the local stack. And it says if it's equal to OX negative C, then jump to main plus 128. All right. Well, it didn't do that, and now it's at error, so we clearly lost. Well, what was that number it was trying to compare it to? Let's see if we can figure it out. Print. And then this is like normal C syntax. RBP minus OXC. And then sorry. Yes, GDB is annoying. I think I have to typecast it as an int or something. Right. Wait, 4? How can this be 4? It just said it had to be 52. How can we have both? And actually what's going on is it was comparing it to 0 before, right? So it expected 0 and it got 4. But like, where did it expect to get 4 from? Where's OXC being set? So you go up here and you have to like kind of follow the chain back, you know. And you see here there's like a little sub here, and the sub here is inside of all these jumps, so you get an idea, oh, maybe this could be a loop counter, right? So it's like subtracting 1 from this variable in every iteration of the loop. And all right, well, how could we do that? So what's the loop doing? Like what's the exit condition? So we get in here, it gets the number, it jumps to 101, and then EAX is our input, remember? It's the return value. So it moves that input to OX10. So we know that OX10 is like our input. And then it compares 1 OX31 to EAX, right? So this is like another condition for the loop. It's saying while OX31 is less than or equal to EAX, continue doing this loop. And this loop is just like the same thing we saw over and over. Add 5 to EAX, move it to the address on the stack, subtract 1 from the index counter. Now, does that give any ideas to people? Do you have like an idea how we could get this to work now that we've seen how the loop kind of works? And so remember that OX10 is the input, and then OXC is the loop counter for the index. And nothing else kind of really matters for the purposes of the loop. That's the only thing it's comparing it to. So are there any suggestions like how you might approach this now? All right, well, I'll give you a hint. The thing it's changing every time is your input, right? Every iteration of the loop, it says add 5 to EAX and store it back to where it came from, and subtract 1 from the end. And the exit condition is OX31 is equal to EAX, right? Which is 49. So the exit condition is EAX equals 49. And we also need the counter variable to be equal to 0. So how can we work backwards from there and find an input that would make all these things true? Right? So are there suggestions for how you do that? All right, well, I'll give you a hint. We saw what the counter started at. It's this guy right here. It's OXC is our counter. So the counter starts at 4, and each iteration of the loop, it goes down by 1. So that means we need to find a number such that if we add 5 to it 4 times, it's equal to 49. And then this is just like a little algebra problem, and you can see clearly it's like 29, right? 49 minus 20 is 29. And so let's try that. Let's see what happens. Not what I wanted to. All right. Let's run it again and see where I went wrong. Or sorry, I said next instead of next I. Next is if you have debug symbols, which we don't. Stop. GDB is so painful to use. It's very powerful, but very painful at the same time.
What you mean? It has the best interface.
I know, right? It's so intuitive, and it shows you exactly how to use it. And
Yeah.
I feel like there's got to be a better tool by now.
there probably is. I just haven't bothered to learn them.
I've got a kind of question. Did you like obfuscate this code or?
No, this is normal code with just without debug symbols.
I mean, did you like in your code, did you put like a for loop and just to make it a little harder?
Nope. The code looks basically like this. And then like some stuff with the input, right? Like assembly is just super verbose, is all.
I got it.
Yeah.
What do you call it?
Like that's all the C code looked like.
Yeah. I was just wondering if it was doing like really weird things on the stack to optimize, because that RBP is the stack pointer, right?
RBP is the base pointer. It says where the previous function is, like where to return to.
Oh, that's weird.
Our SP is the stack pointer.
It's using that like a register, or like an actual address.
Yeah.
Function.
Yeah, it's so registers are just like data, like they just hold an integer, and so in assembly, like the difference between integers and pointers is like kind of sketchy. Like you can just add 1 to a pointer, and it's just like a numeric operation, like anywhere else.
Well, that's any assembly, right? Because it's just. I'm just surprised that it's using the base pointer and not the stack pointer for that.
Yeah, well, the base pointer is like changed what it does several times in the history of Unix, but I don't remember what it's for now. Yeah, so see here we subtracted 10 from the stack pointer, and now it's different from the base pointer. So the stack pointer is like where our locals start, and the base pointer is like where it was originally. So it knows how to get back to the previous function. So let's try this again and see why 29 didn't work. Let's skip all this stuff. When we get to input, let's put in 29 like we thought would work. All right, and it loads some stuff. and it sees that 29 is not equal to 49, so it keeps going in the loop, right? And it adds 5, and it keeps going. And notice how we can like see it being updated in every iteration, right? It's kind of useful. All right. And then finally it gets here, and 54 is bigger than 52, so it stops going through the loop and it exits. All right. And then this was the compiler being dumb. It didn't realize that we already had EAX cached, so it moved it from memory to the register again, even though it didn't have to. All right. And then, okay, so I was too high. I said 29, and it should have been 27. Notice how this says OX36, and this says OX34. So we're exactly 2 over. So let's try this over again. And then I'm going to disable the breakpoint because I don't need it anymore. Right. Yeah. Why did I set 2 breakpoints? All right. And if we try 27, it still doesn't work. All right. Clearly, I'm doing something wrong with my life. All right. Let's try this again. And so I forgot to set the breakpoint. And we don't actually have to stop at the start of the main function. We can stop anywhere within the function. So let's try that now. This is way down in library functions that we don't care about. All right, so here's main again. And I'm going to stop exactly at the scanf, because that's the one we actually care about. So let's say break at that address. And this is like the instruction address. And it's going to go ahead and do that. I'll say disable 1 because we don't need it anymore, and run this over. Okay, and see how it stopped exactly before that call queue, exactly before it read the input. And so we tried 27 before, and it didn't work. And let's see why it didn't work. Oh. Ugh, I hit next again. This is annoying. So this is like kind of a tedious thing, right? Like when you're reverse engineering something, you have to go painstakingly, like one assembly instruction at a time. There's tools that make this less painful. I think I'm sure Ronnie knows. It's if I could spell, wow. Anyway, there's like a bunch of tools to do this. If you IDA Pro, that's the one I was thinking of. This is like the one professionals use, and it costs a ton of money, and you can like actually visualize the source code without staring at hex numbers. So if you were like actually doing this for a job, you would probably use something like IDA Pro. But I'm a student and I don't have money, so I use GDB. Right, so we're back here. We've got 27. And it jumps. All right, and let's see. We go through here. We go through the loop. All right, we get to 52. And it compares it to x34, which is in fact equal. And it gets down here, and it compares 0 to the counter. Well, what's the counter? We had it before. If I can find it. Here it is. Oh, it's -1. So we did this too many times. It subtracted 5 times instead of 4. All right, well, that tells us what we need to do. It needs to be 5 greater. So let's run it again. C is for continue. And there we go. And now we got it. Questions on how I did that and how this assembly thing works and how GDB works? Is the silence because you're not interested or you don't know where to start asking questions?
So they don't teach debugger with 145 and 146 anymore?
No, they don't.
Well, JJ did the debugger in 146 a little bit.
I think
Yeah.
it was too much. Like a brief introduction.
Yeah, it was like
Yeah.
one class.
Yeah,
Like,
I took it last
debugger.
spring and we used it actually relatively frequently, but that was when in person. Yeah, the last time JJ taught in person, we covered the debugger for 146.
I mean, that's good. When I did 145 and 146, it was like 30 years ago, and we were learning in Pascal on Macs. And
Oh, wow.
that's a very structured language, strongly typed. It's a perfect teaching language, and the debugger was built in. And as they taught us the language, they taught us the debugger. Super, super useful. And that was the last time we used Pascal. It was like the very next class, they just threw you into C whether you knew it or not. And, you know, printf school of debugging at that point.
Right. Yeah, it's the debuggers for C are like working at kind of a low level. It's you can have debug symbols to try and get. So let me give you an example of what this would look like if we had debug symbols and we actually knew like what the variables were named, because it's a lot more pleasant. So here's printf source. I think this is it. Oh, all right. So I did not compile this with debug symbols. So this -g means give me debug symbols for the source code. And then if we run GDB on the program here, right, and so we can actually see like what's going on now, right? Like you don't have to say print at this assembly address. You can say break at line 15 and that sort of thing. And it's like a lot easier to use.
Oh, does this add, I wonder what the difference of the assembly, or what the actual, like, binary says.
Oh, like how much space the debug symbols take up?
That as well, because, I mean, what do debug symbols look like in x86 code?
Yeah, so x86 instructions are different from debug symbols. So debug symbols are dependent on the format. In this case, the format is ELF.
Oh, right?
Is
Yeah.
executable linker format, I think. And ELF is part of your, when I keep saying toolchain, I don't mean like the OS and stuff. I mean the linker and the compiler and the dynamic linker all working together. And so ELF is like the format, this shared format that they know how to read. And so not stripped means that it has debug symbols, because that's a reasonable way to say it has debug symbols. And so you can say, you know, give me back the symbols in this program, and it has all these variables that you can look at.
That makes sense. I that was brain fart.
No, you're good. It's a good
I
question.
don't know why I thought they would actually go down to assembly. But that's very neat. I guess if everything gets compiled down to ELF, then you should be able to use like a debugger on any outputted program, right?
Well, not everything is debug symbols,
Yeah.
but yeah, you can run a debugger on any executable or any shared object even. If you remember, we stopped in the middle of fwrite. Fwrite didn't have debug symbols either, but we could still look at the code that was in there. Let me do an example of that. So we can do break fwrite. And you can see here we're like way in the guts of iofwrite.c, wherever that is. It doesn't know, and you can like step into it. And we don't actually know what's going on because the debug symbols are missing. Actually, this looks like it does have the debug symbols, but it doesn't have the files to go with them. That's interesting. But anyway, yeah, you can step into any object file. Other questions?
Yeah, I'm not exactly sure how to ask questions about it, just because I don't like have any experience with like working at this low of a level.
Mm-hmm.
Until I take 212. I think that's because I literally just looked on I'm taking it next semester, so I guess that'll definitely help. But I can kind of piece a few things together, what you're saying, just because from C, and I don't even really know C, I just know C++, but it seems pretty similar, but at least on the surface, obviously. But yeah, I don't really know how to ask questions about it quite yet.
Yeah, it's like a whole different world, you know. It's you have to learn how things work under the hood.
I wouldn't even sweat it. I don't know much of this at all either. I just know Josh, and that's good enough.
Yeah.
And
But
I don't remember most of it, and I don't use it in my daily day-to-day life because I don't like programming. So yeah.
Yeah. I think one big plus for Josh is that he's written a compiler that compiles to x86.
yeah,
So
oh
he's
my
been-
god, I've had so much trouble debugging L-vals. L-vals are the bane of my existence. Oh my god, let me pull up this issue. You can see like the 6 hours I spent on it that day. But yeah, it's when you're writing a compiler, you have to like really care about all this stuff. I think it was treating an array as a pointer.
And another cool thing about Saltwater is, I don't know if Josh put it on Brew, but it's on all of the major package managers.
I think it's only on Brew. It's definitely not packaged with apt. But
Oh.
So did you have to reference like what was the compiler for?
oh, this is just me having fun.
Oh, okay. Because I was reading up on like the fact that there's no like official, I guess, documentation, if you will, for like C or C++, but rather it's just like a manual, or not even a man. I don't really know what the word would be, but like it would only be for people building compilers that you would reference.
Yeah, so
that
C
text.
has a standard instead of a reference implementation. And
Right. Yeah.
yeah. So the standard says if you build a compiler, this is what you have to do. But there's no like simple version of the compiler that you can look at and take apart. It's all, you know, playing your GCC or TCC. There's no reference compiler.
And that comes from its history. It's got a really neat history.
Yeah.
Like most languages are really just I mean, even Python has a strict grammar, strict rules.
Well, I don't know if I'd say that.
Well, like
Python definitely has a reference implementation and not a standard.
yeah, like C++ and C, or at least C++, not so much C. It's I think like 50 years old, 40 years old, and it's just gotten really a lot of baggage.
Yeah, C++ and C both have a lot of backwards compatibility, let's say. Yeah, so this one's here. This is a little fun part of C, this bug here. So say you have like some array here, it's 1, 2, 3, whatever. And you say printf, you know, some digit. You don't have to say A1. You can also say 1A. And it means exactly the same thing, and it's valid code. Which is kind of crazy. And the reason this works is because arrays in C are actually just pointers, and pointer arithmetic is commutative, which means if you treat the 1 as a pointer, and you add A to it, that means it's the same address.
Is that because it's not object oriented? So every what would be an object is just a pointer.
Well, not everything is a pointer.
Okay.
It's because C has like kind of loose rules more than that it's not object oriented.
Interesting.
Like for another weird example of this is that you can add characters to numbers, and it just works. And there's like no warnings or anything. Like this warning is about the variable being unused. So C has implicit conversions like this all over the place. I could rant for hours about how much I hate C.
And I think those still hold in C++ because
most
as
of
much as
these
I understand,
Most of these are still in C++, yeah. There's one thing which is not, which is functions without a prototype. So, fun fact, you can call this function with arguments. You can say f of 1, and the compiler will just let you do that. And it's like, oh yeah, I guess that works. This is with wall, by the way. If you run it without wall, then it will not warn you, which is kind of crazy. Why did they decide to make that position dependent? Okay. Oh, I'm surprised that did warn. Well, good on you, Clang. That's an improvement. but yeah, there's a lot of warnings in C that should be errors.
Wait, so what happens when you run it then?
Well, in this case, it does nothing because int f does nothing.
Oh yeah, but
But in general, so this is left over from pre C89 where there were no prototypes and you couldn't say int I, and what you would say instead was int f I, like that.
ew.
Yeah, it's and then you could like leave out the I and it would let you do that, and it's ugly. Yeah. Oh, interesting. You can't do that. You need one or the other. And anyway, C has lots of baggage.
I feel like you could give a talk on that by itself. It looks like
If you guys want me to give a C talk, I can give one for ACM. I'm happy to.
it's yeah. I mean, I think it's super interesting personally.
Yeah, I like it. C is like a neat language. It's really simple, but also really easy to shoot yourself in the foot with.
In my opinion, C should only be reserved for like drivers and the very bare minimum of operating systems.
Right.
It's also common in networking devices.
I like C.
I do too.
It's my favorite out of all the ones I knew. Y'all are just C bashers.
C has a very nice specific niche, which is doing the things that no other languages can do, and other than that, I don't like it. It's too simple. There's no guardrails.
Rather use
Exactly.
C
That's what I
sharp.
like about it. I freaking work as SU minus.
Yeah, but when you have like mission critical stuff, like
Just gotta learn to program. That's all.
Right. Well, right. I had another talk about that. Is C's approach is do it right the first time, and it's not a great way to write secure software. So I'll put a link to that.
I'd rather
too.
use C than Visual Basic, that's for sure.
Other questions about assembly? I know we kind of got off topic for a bit there.
I don't know if this was answered at all or even discussed, but did you talk about the difference between jump and branch? I know x86 doesn't use branch language, or
Yeah,
maybe
so
it does.
jump is an unconditional jump, and branch is like a conditional jump. Jump if this condition is true. And so if you saw all those jump equals before, those were branches. Those were conditional jumps.
Okay.
Yeah.
I have a question that I mean it might seem silly, but like I don't really care. And it would just be like, so there's not like really like you're not gonna really working with an interface that's specifically like maybe like in the older days, but like today, like you're doing this all through like Bash and GDB as opposed to like having assembly having its own interface.
Yeah, so assembly doesn't have an IDE, but there are tools for working with it. Like, it's not that they don't exist; it's that I don't use them. You can have like an IDE or whatever for working with assembly. It's just there's not a ton for writing assembly because not a ton of people write assembly anymore. It's mostly for reading it. Does that answer your question? I think my computer might have frozen.